One thing I find a lot of students have trouble with is t-crits and alpha values for p-value. Now I'm not going to go through the conceptual background of probability distributions and all this stuff that makes these things exist, but really I'm just going to show a way to remember what a t-crit means and a p-value alpha means with regard to making your conclusions about your statistics. So specifically, we're talking about our t-crits. Sometimes it's a z-crit or other crits, but that is the same concept. And then our alpha value. Now our alpha value is just a p-value. Now, the idea of these numbers is they're a threshold. What that means is if we pass that threshold, then we're going to call our two groups or whatever we're looking at as different things. So if we have group 1 and we have group 2, and they have whatever values they have, we're interested to see if group 1 and group 2 are equal or not. So at some point, someone said, we're going to create a criteria that indicates that if it's past this criteria, we are going to call them different. But if it's not past this criteria, we're not going to call them different. They're going to be the same thing. And really what it is we're going to calculate things like a t-score and a p-value. And these are going to be our observed values. So what the difference between these are these are our thresholds, and these are our actual observed calculated values. And we're going to compare the t-crit to the t-score and this alpha value to our p-value. But let's talk about this using an analogy. Let's say we have someone running a marathon. So what we have is a start position. And we have our lane, which is what they're running on. And then we have a finish position. So the distance between the start and the finish is pre-specified. So let's say it's 10 kilometers. Let's say an hour goes by, and we want to know if our runner has passed the finish line or not. So because we can't run the 10 kilometers ourselves, we use a GPS tracker. So after an hour, we check our GPS, and we find that our runner is at 7 kilometers. So what that means is our runner is around here. So after 1 hour, our runner did not finish the race. Now let's consider a different situation. What if our runner, after 1 hour, was instead 11 kilometers from the start line? What that means is they're over here, and they have finished the race. So they're past the finish line. So there are a lot of parallels between this running analogy and our t-crit value. So for example, the finish line is our t-crit value. If I tell you that our t-crit is 1.96, that means the distance between the start line and the finish line is 1.96. Now, the t-crit is something we determine before we run an experiment. So we don't have any observations, we don't have any data yet. The runner has not started the race, but we first designate how far the finish line is, or where the t-crit line is. Just like it was for the runner, once we do observe data, we then determine where the runner is and whether they've passed the finish line or not. Or in other words, whether they've surpassed this t-crit or not. And the runner is our observed t, or t observed. Now what this means is our t observed, if it's past the t crit line here, then our two groups are different. So group 1 and group 2 are not equal. But if instead our runner is over here, and that's the t observed, they have not yet passed the finish line, and the groups are actually then equal. So there is no difference between groups. It's not statistically significant. Now let's use an example here. So a t-crit of 1.96 is a common one, and I'm not going to get into why that is right now. So what we have to do is we have to calculate our t-observed value. But how do we do that? Well, we use the equation of the t-test. So we take our mean minus the mu, and this is a population parameter given to you by the question, divided by our standard error, where our standard error is our standard deviation divided by our square root of n. So I covered this in another video, and I'm going to look at t-tests a lot closer in a different video. But the idea is we need to calculate our t observed, but our t-crit is something we determine ahead of time. So let's look at this in the sense of we have a t-crit that you've determined ahead of time, and that's to be 1.96. And then through statistics, you calculate a t observed. And let's say that t observed is 2.00. Now the question is, if the finish line is 1.96 here, and the runner is at 2.00, is it past the finish line or not? Of course, the answer is yes. Our runner is past this finish line, or it surpasses the t-crit. In a different example, what if our t observed was rather 0.56? So again, the finish line is at 1.96, which means our runner is a lot behind that. So let's put our runner back here, maybe. So have they passed the finish line? And the answer is no. So they have not surpassed this t-crit, which means our two groups are equal. Hopefully that's starting to make sense. That's just half the story, because not only do we have to compare our t observed to our t-crit, but we also have to compare our p observed to our alpha value. Now the good news is you only need to really figure out one of these two things, because if the t observed is larger than the t-crit, so our runner has finished the race, it means that we have found that there are differences between our groups. And what that means is the p observed is going to also indicate that there are differences between our groups. So this comparison between t observed and t-crit is always going to lead to the same conclusion as when we're comparing the p observed to the alpha. Now what that means is you really only have to determine one of them, and we most often find that students have an easier time determining the difference between t observed versus t-crit because we want our t observed to be bigger than our t-crit value. But the p observed, we want it to be smaller than our alpha. So let me write that out. Our t observed, for something to be significant, or our groups to be different, t observed is going to be greater than our t-crit. but our P observed needs to be smaller than our alpha. And just as we discern what the t-crit was ahead of time before the experiment, we also discern what the alpha is. And most often in statistics, especially in statistical courses, we use a alpha of 0.05. So what that means is for something to be significant, for two groups to be determined to be different, our P observed value needs to be smaller than 0.05. So for example, 0.001 is a smaller number than 0.05, which means it'll be significant. So if we focus on our P value, we can think of this in a different way. So after the finish line, we have, let's say, a fan. And this fan gives off cool air. So a marathon's hot, which means our runner is going to be very hot. Let's actually put this all the way here. So rather than using our T observed values to determine whether our runner has passed the finish line, we could see how far our runner is from this fan to determine our P observed value. So what this means is that our P observed here is going to be our alpha value, which I wrote down here is normally 0.05. So we could think of our runner as the distance between this fan and them. So the distance between the fan and the finish line, let's say, is 5 meters. But then the distance between the fan and the start line is something much bigger, let's say 100 meters. What we want is we want to see if our runner is within 5 meters of the fan or not, because that'll also tell us if he's past the finish line. So what that means is the smaller the distance between our runner and the fan, the more likely that we have differences between our two groups. So if I say our runner is within 3 meters of our fan, that means he's within the area where the fan is cooling off. So he's cooling off from the fan. It's not quite at the fan yet, but he's well on his way. And furthermore, he's already passed his finish line, because really all we want for him is to feel the fan air. And he could do that as far as 5 meters from the fan, but he's a little bit closer than that. If I say instead, our runner is 10 meters away from the fan, what that means is they're about here, and they're unable to feel the cool air of the fan. And what that means is they haven't passed the finish line. So our two groups in this scenario are equal. There is no difference between them. But in a scenario where they're in the fan, or in the air of the fan, our two groups are different. Now, one thing that throws students off is just the idea that p-values range from 0 to 1. So what that means is we're usually dealing with, or we're always dealing with, these decimals, like 0.05. So what I just was talking about is 5 meters from the fan. So instead of that, we can say, well, our alpha value is 0.05. And this is our alpha. And that means that if our p-value is smaller than 0.05, our runner is within the range of the fan. And our two groups are different. But if our runner is greater than 0.05 from the fan, they're going to be over here not feeling the effects of the fan, which means our two groups are the same. So if our P observed value that we calculated using both the t-score and then the t-table is 0.035, for example, that indicates that our runner is 0.035 distance from the fan, which puts them at around here. Which then means that our two groups are different from each other. They're significant. If we rather compute that our P observed is 0.1201, for example, then they're 0.1201 distance from the fan, which means they're around here. And they haven't yet passed the finish line, and they don't feel the effects of the fan yet. What that means is our two groups are equal. Regardless of whether we use the P value or the T observed value, if they've passed the finish line, or if they're in the range of the fan, we say that our groups are significantly different. If they haven't yet passed the finish line, or they don't feel the effects of the fan, they are not significantly different. So here, our group 1 is not equal to our group 2. And here, our group 1 is equal to our group 2. Now to reiterate, if we find using our T observed and our T crit value that there is a significant difference between our groups, our P value versus our alpha, P alpha, will indicate the same decision. So they always lead to the same decision. So really, if you can determine one of them, you can determine both of them. One final thing to note, or to clarify, is where we get all of these values. Because we start with a T crit and a P alpha. But we also have this T observed and this P observed. And the question is, where do all these things come from? Well, really, we can split this up like this, where these two come before the experiment, or I'll say before data, and these are computed from the data. Now, I could go into how we figure these out before the data, but for now I'm not going to. That can be left for another video. The idea here, assuming you know how to determine these things and to compute these things, you can now start making these decisions about whether our data is different between the two groups or not.